High temperature solids you have done in your high school, and that you know that specific heat goes CV goes as 3R from this is from classical vibrations that was done before quantum mechanics, and this is called Dulong-Petit's law. However, when one calculates its measures its specific heat against temperature, one before people had up to this, and that is sure enough Dulong-Petit law 3R. But when you go to low temperature, this goes like that. That means these experimental results become available after low temperature studies were becoming available in 1917, 18, 1920, and around that time this remarkable departure from classical statistical mechanics. This is just one of those beautiful things that happened, starting with blackbody radiation, photoelectric effect, Balmer series, quantum, all the beautiful things. So breakdown of specific heat at low temperature immediately drew huge amount of attention, and people couldn't do it. People couldn't solve it. Because they didn't have the energy levels. However, these Schrodinger solution of the harmonic oscillator and energy with n plus half h nu, they came available in 1926, 1927, and then at that time these beautiful departure from classical mechanics, it was done by Einstein. What did Einstein do? And then corrected by the, and that became to known as the Debye-Einstein or Einstein-Debye theory. So what Einstein realized that the solids has many low frequency modes. They are low frequency in compared to, this is a very interesting, they are low frequency with respect to atomic vibration, but they are not that low frequency that you can treat them classical mechanics. So there are frequencies which are normal modes. So basically, when I have consider one dimensional model, you do Kittel or Ascot Mermin or all the. So we have this chain, linear chain. Then the Hamiltonian is the vibration, this vibration, this vibration, this vibration, this vibration, n number of vibrations, let us say. Now these modes are this position of these molecules x1 minus x2 square plus x2 1 2 3 4 5, they are in terms of atomic position. Goes like that, right? Now I can make a, so when I expand that, the x1 square, x2 square, x1 x2, x2 square, x3 square, then x2 x3. Now I can make a coordinate transformation which is same as diagonalization, where I go to representation where, since x1 x2 is a linear coupling, and this is very important, and I don't need to go to it, but non-linear I cannot do that, but in linear coupling I can diagonalize this, and I go a new set of vibrations. Those vibrations are now is collective vibration. That means it is like in water we have a collective symmetric stretching or asymmetric stretching, where oxygen remaining the same, but two hydrogens are moving together. Okay. Similarly here, all the molecules, atoms are moving together. That means there is a kind of this vibration, all of them moving together. They are like sound waves, and their compression and their reflection, and they are, some of them are like this, others are going like that. So just like symmetric asymmetric stretching in water, there are many 3n minus, if it is a linear case, 3n minus 6 vibrations are coming in. So these are the collective modes when you get by diagonalizing the Hamiltonian, and where collective the molecules are moving together, and these are low frequency modes. And then these low frequency modes, as I told you, they are low enough frequency to contribute enormously, significantly to entropy and to specific heat, but they are high enough such that you cannot contribute them to classical mechanics. When you go to high temperature, then these modes, low frequency modes, can become treated as quantum mechanically. But when you go to low temperature, this is temperature I am talking of 0 Kelvin, temperature in Kelvin. So in this region, so maybe at 300 Kelvin or 200 Kelvin, you can still have the Dulong-Petit's law, but when you go to 10 Kelvin or 5 Kelvin, then those low frequency modes has to be treated quantum mechanically, and they make a very important contribution. And that is now the Debye-Einstein famous theory, which first Debye did it, Einstein did it, and has a exponentially to the power minus t dependence. What Einstein made, he did not do all this diagonalization or anything. He just set all the frequencies of the solid. He got the total number correct. All they have the same frequency, constant frequency. That's called Einstein frequency. Then this is very easy. Then you go to Einstein frequency, and you can now calculate the specific heat from there. All of them same by ds dt. Debye did it rightly. Debye took care of the what we call frequency dispersion, that all these modes are of different frequency. They have a lowest frequency and highest frequency. When he did that, he got the real value, it is as t to the power cube, famous t to the power cube law. But that came out essentially from just what we are doing here. Okay, so this is specific heat T ds dt, and then when I do this from entropy, then I get this expression h nu by kb square. So this is the entropy. I take derivative, I get one term from here, I get two terms from here, I can combine them, and when I combine them, you get this expression. You can check it out. It's a trivial from entropy, this is really trivial thing, so I am not going to do it, but believe me that this is the expression that comes in. This is the specific heat of the one harmonic oscillator, one harmonic oscillator with frequency nu. Now in go to solid, so it is shown by, as I read in Einstein, later by Debye, these expressions where harmonic oscillator plays an important role in specific heat of solids at low temperature. So high temperature we go to Dulong-Petit's law, but low temperature we now, in order to calculate, make it as frequency dependent Cv nu, and then we have to integrate with the density of states G nu, then Cv nu, and this is what Einstein did. And Einstein said, okay, I can have only all the frequencies are one, are the same, identical. Then I have n number of vibration into then Cv nu vibration, nu Einstein, and then I put that nu Einstein here, and I get an exponential dependence as Einstein showed in this region. However, all these vibrations do not have the same frequency. They have a maximum frequency because of the wave is acoustic wave. They are essentially waves that you can accommodate within this thing, and so that extra consideration becomes important at even low temperature. That gives to TQ law. So this is a really interesting thing that happens in 1930s. I think 1932. or around that time that Einstein did, and then Debye corrected Einstein. So, the statistical mechanics of harmonic oscillator plays such an important role in doing this. So, now continue. So, the next we will do now the rotational partition function. This is the vibration, and as I said even very recently, even today many people are doing those entropy, those specific heat to consider amorphous solids, these or low temperature liquids. For example, we ourselves did a work, as I told you last year, with one collaborator, Professor Shinji Shaito. Long paper came out in Journal of Chemical Physics. We used these things to calculate the specific heat and entropy of low temperature water, and that seemed to explain several things. So, it is many people are using these things. So, they are not just so, just like in quantum mechanics, the vibrational spectra, this Schrodinger solution and the harmonic oscillator plays a very important role. It's something really surprising that such a simple model and kind of artificial model plays so important role, but that happens in physics again and again. That is why harmonic oscillator model is very much cherished. That is very loved and liked by scientists, because they can use in many different situations. Similarly, now it goes as like that, translation, like that, vibration also, all these things are very important. Now, rotation, that is why we are repeating it. Now, we do the rotational statistical mechanics of rotational mode or rotational motion. We did translation, we did vibration, we said electronic is not important, but rotation is important. Now, rotation has a place which between vibration and translation. In translation, we got away without doing quantum mechanics. In vibration, we had to do quantum mechanics. But in case of rotation, it is in between. So, rotational energy levels, if translation energy levels is spacing like this, very continuous, then and rotation will be like this, vibration is like this. So, this is where we are somewhere in between quantum and classical. So, we will see that in low temperature, these energy discreteness, the quantum nature of the energy levels, the discreteness plays an important role, but in a high temperature, you can be like one like classical mechanics. So, let us do now again Schrodinger solved for a rigid rotator. A molecule is rotating with a moment of inertia I. Moment of inertia plays the role of mass, So, the moment of inertia I, this is the energy levels that again that Schrodinger gave us. Ej is j square j plus 1. But there is a very important thing now, which we never faced before, that these energy levels are degenerate. So, now before we are talking of individual energy level, they are not degenerate in particle in a box, they are not degenerate. In a particle in a box, they are degenerate in a different sense. That means I can have x, y, z, I can 0, I can have 1, 1, 1, and there are or I can have 1, 2, 1 or 1, 1, 2, but we just sum them up because as they decoupled. Actually, if we take up that, it becomes more complicated. But in rotation, even for a single rotation, we have the degeneracy, which is 2j plus 1. Then partition function goes over, you sum over these energy states which are given by energy Ej, and then we have Gi e to the power minus Ei by kVt. So, instead of each energy level, we count the energy states. That means, okay, this energy state is E1, but I have 2j plus 1 of them. So, then this thing is 2j plus 1 and this Ej is this quantity. So, my partition function now becomes this quantity. My partition function now becomes this quantity. and I will tell you that again why it plays an important role this case also. So, now q rotation is 2j plus 1 e to the power minus ej by 2k by kbt, and then ej, I put the ej here, and then I get these. Now, I noticed something very interesting. Till now I have been doing very mundane and very simple substitution, but now I can be a little smart. I realize the 2j plus 1 is nothing but a derivative of j into j plus 1. So, 2j plus 1, if I take d by dj, j into j plus 1, then this is d by dj, j square plus j, and that is 2j plus 1. So, this quantity is nothing but a derivative of j plus 1. Say then I be little smart, I do d by dj, but however that brings out many other quantities, 8 pi square I k b t by h square. So, I have to cancel them. So, I put them in form 8 pi square I k b t by h, this quantity is the same as this quantity. But that has been now very nice. Okay, I made some progress. I cannot evaluate this sum exactly, which is a pity, really pity, but we cannot do it. Many times you will see some very simple things we cannot do. Maybe some of you can be smart and do a better approximation in this case, but we have not been able to do. So, then I can write 8 pi square by from here 8 pi square I k b t by h square equal to d r j, and I define this function r j as, because it is no point of writing it again and again. So, I find r j as this quantity. So, this is my partition function, rotational partition function. That means this then is so rotational partition function. This is my rotational partition function. Let me see what I can do with this now. As I said, for many molecules, this is particularly important for physical chemists, that where we have the rotation. And I remember when I was doing postdoc at University of Chicago with the James Franck Institute, and there are some fantastic group of people there, and there are some guys who made history, and there are people like Stuart Rice, Don Levy, and they were doing spectroscopy in the gas, and there was a lot of excitement to detect the rotational level dependence of electronic and vibrational relaxation. And this was the reason. They have the partition function, they know how to, they know this thing is there. So, if a molecule rotate very fast, then they will modify the coupling between different energy levels, and then we would be able to see in the temperature dependence of relaxation, vibration relaxation, rotational level dependence, that would not be otherwise if the vibration rotation coupling is not there. Okay. So, let us go ahead and do some little bit more of them now. Okay. So, important thing is that, it's a very important comment here, the strong dependence of partition function on moment of inertia. As I said, this plays a very important role, very important role in energy relaxation, in vibration energy relaxation of A. So, then low temperature we go to T going to 0 limit, then this quantity, if I go to low temperature, then J by J plus K, this term low temp T is small, and then J equal to 0 of course survives, but J equal to 1 is this 1 into 2, then 2 by this IKBT survives, and then next one when J equal to 2, that becomes 2 into 3 6, but then T is small, so the exponent is large. So, larger J terms gets cancelled. when you do that term, then you find low temperature is enough to keep one term, that is j equal to 0 comes with 1, that j equal to 1 is enough. So, you get this quantity. So, at low temperature, temperature going to 0 Kelvin, I do have a simplification which is this term. Now, the partition function is 1 plus 3 by these things. A similar simplification happens in the high temperature also. Now, high temperature energy levels are continuous like in classical mechanics. That means J into J plus 1 by kBT, temperature is very large, they get high temperature, they get squeezed, they are very close to each other. Now, I can replace this sum by an integral. If I replace this sum by an integral, then I can do that integration, because I already have that interesting thing that this guy is a derivative of this guy. So, it is just an integration dx d by dx. This is the integration. I can do that integration and then it is trivial, and I get this quantity 8 pi square I kBT by h square by t by theta. So, this is this theta is theta r. So, I have now a very nice partition function high temperature that is proportional to and I define a rotational temperature just like before, that is h square by I kBT, because this quantity partition function is dimensionless, must be dimensionless. So, this quantity is the inverse of temperature. Then just like in vibration, I define rotational temperature. This is something one has to be a bit careful. I said a very important thing here, that partition function is dimensionless, and so dimensionless q, because it is sum over energy levels. So, this is number, exponential is a number. So, q is a so when we did the translation of vibrational function, the quantity that makes this dimensionless is lambda. So, you have to be very, very careful, lambda, but de Broglie wavelength, and de Broglie wavelength comes again and again, and that comes through this Planck's constant, and all this combination h square by lambda kBT and that together for the de Broglie wavelength, that plays a very important role in in the quantum classical analogy. So, in the when the Boltzmann and Gibbs did, they did not have the Planck's constant. So, they left their partition function with a volume term, and that then they were reconciled as this is the volume of the cell in the phase space and all these things, but you do not need that really. You have to, for bookkeeping, you do not need the physical interpretation, but because there is an exact expression. Well, you can go ahead doing a physical interpretation like Richard Tolman did a lot of it, and that probably helps in certain cases, but you do not need that. So, now I have the beautiful expression of the rotational partition function, which 8 pi square I kBT by h square. This is my rotational partition function. So, I have the translation of my partition function, I have the vibrational partition function, I have the rotational partition function. Now, I go the rotational partition function calculate the free energy in the particular high temperature limit. So, this is the high temperature limit. High temperature limit I do kBT L N Q and then kBT L N Q rotation, and then I get this quantity, and then I get the free energy as I look at that, then it is T by theta r, and because the T is the numerator, theta is the denominator, theta defined like that, that has to be careful about that. And then minus kBT, then this theta r is T by theta r. So, there is a minus, or you can write theta r by T. Okay. So, free energy is this is the free energy, then we can calculate the other quantities like entropy, and this is important, as I told you, that when you are going to talk of low temperature and up in the cloud, the entropy of water molecules, entropy of a linear molecule. Now we are doing diatomic, we will do polyatomic very soon, but we get the these are the quantities we need. So, entropy is now a function of moment of inertia, entropy of molecule, moment of inertia I, and the expression is by taking the derivative of the, we get this quantity, because this quantity before that, and there is quantity, there is a temperature here, there is a temperature here. So, two terms come out now, entropy, and these are the two terms. Beautiful expression of that entropy is nkb, which is the entropy unit, in of course is extensive n number of particles in non-interacting rigid rotators. So, kb 1 plus T by theta r, ln theta r is the entropy. Now, we get the specific heat, and the specific heat T ds dt, we take the derivative of that, there is no temperature here, there is only temperature here. When you do that, ln, it comes T by theta r in below, and the theta get cancelled, and you take a derivative, and T, this T, it becomes 1 over T, and this T cancels to 1 over T, and you get a beautiful expression, just like in ideal gas, that specific heat is nkb. And so, this is the thing that we really wanted to tell you, that next, in the next lecture, we will start with the polyatomic case. We will finish the diatomic completely. We calculated entropy of rotation, with vibration, translation. So, but as I again and again telling, these are very, very important things. These, even though they are non-interacting limit, they go on the backbone on each interaction is built in, like virial equation. So, we start with ideal gas law, and we add in attraction, and that is the virial equation of state. Okay. Then we start with the harmonic oscillator model, we put an harmonicity, and so we add the correction term to that comes from ideal gas law. This is the way statistical mechanics is built up. Actually, that is the way quantum mechanics is also built up. That is your perturbation theory, that you want to talk of harmonic oscillator, but the transition vibration, you need a perturbation. Otherwise, they are eigenstates, they do not talk with each other. So, the interacting system comes with the perturbation. Sometimes when the perturbation does not work is where things are really interesting. And so, the next lecture will start here, the polyatomic systems, and then we will go on doing some very, very interesting stuff. So, stay tuned. Thank you.